for gases to move from one place to the next, they must go down their own concentration gradient, their own partial pressure gradient. So what we first need to do is highlight what is the partial pressure of oxygen and carbon dioxide in the pulmonary artery coming through. So let's have a look. If we have a look first of all at, let's do oxygen. The partial pressure of oxygen here is going to be 40 millimeters of mercury. That's the first thing. Second thing is the partial pressure of carbon dioxide coming through is 45 millimeters of mercury. So I want to highlight an important point here. Anytime gas moves from one point to the next, it must go down its own partial pressure gradient. So I like to draw it up as a slide, for example. So here's a slide. If we've got the highest concentration of oxygen being 104 up here, that's the alveolus, and down here it's 40, you can see it's quite a steep gradient. Oxygen will move down the slide. Costs no energy, that's just what it wants to do. Let's have a look at carbon dioxide. We know it goes from here to here. So its highest concentration is here in the pulmonary artery, and its lowest is here in the alveolus. But look at the difference, 45 to 40. So it's not as steep at this one. So let's draw it up. We've got the slide, and it's not as steep. So we've got 45 here and 40 there. Again, it's still going down a concentration gradient, but like I said, it's not as steep. Here's an interesting point. Even though the partial pressure gradients for oxygen and carbon dioxide are very different, the same amount of oxygen and carbon dioxide is exchanged at the alveolus here with the pulmonary capillaries, the same amount. Now, why is this the case? This is why. Carbon dioxide is 20 times more soluble than oxygen is. So carbon dioxide wants to cross this respiratory membrane. It wants to. Oxygen, less so. The way I think about it is like this. Even though it's not as steep here for carbon dioxide, it really wants to go down that slide. But here for oxygen, it needs a push. Someone needs to push it, first of all, to get down that slide. So that's why. Carbon dioxide, 20 times more soluble across that respiratory membrane. All right, so as this blood goes past, think about this. That right ventricle, it's going to contract and it's going to push blood out of the right ventricle at 4 liters per minute. This is what we call the cardiac output. Importantly, the left ventricle is going to push blood out at 4 liters per minute. Again, cardiac output. So the equivalent amount of blood being pushed out of the left ventricle is going to be equivalent to the right ventricle. Every minute, 4 liters is pumped out. Now, this 4 liters is just going to the alveoli to get oxygenated and to remove that carbon dioxide. And the way I think about it, amazingly, is you end up, this branches off, these pulmonary capillaries, you end up having around about 280 billion pulmonary capillaries, which are feeding, or I should say, which are articulating and hugging the surfaces of around about 400 to 500 million alveoli. Huge. Together, you add up the surface area, the possible surface area for gas exchange, it ends up being around about 70 square meters, around about the size of a tennis court is possible there for gas exchange.